So next, let's talk about some of the theoretical analysis and what are some of the concrete kind of things we can say about this sort of application more generally. So first, before we do that, let's review some of the variable definitions just to kind of normalize everything here. So K is, again, the subspace dimension. M is the number of compressive measurements. Theta is our standard parameter vector. Capital theta is the parameter set. Capital D is the parameter dimension. N naught is the base covering that we'll define more rigorously in just a moment. V theta is our parameterized orthobasis, and script S theta is our parameterized subspace, which is just basically the span of V theta. Okay, so in order to kind of formalize everything, we have to talk about geometric regularity. So we're talking about how big, in some sense, our parameter set is, and how we can kind of connect these different parameters in this function together. Okay, so one natural metric that will come up very often is the subspace metric. So you can define a distance between two subspaces as basically the spectral norm of the difference between the projection matrices that span these subspaces. Okay, so in some special cases we can have Lipschitz continuity of this metric, and we can relate this to the Euclidean norm of the in the parameter space, basically. And in some cases, we don't have Lipschitz continuity, but we have something more general, which is called Holder continuity. And this is basically just saying that it's Lipschitz continuous up to some power gamma. And generally, for our cases, gamma will either be 1/2 or 1, just to give you an idea. But the main idea here is that we can connect the regularity of S theta to the simple regularity of just capital theta in terms of these covering numbers. So what is a covering number? So basically, if you imagine trying to cover this rectangle, this dotted rectangle up here, how many circles or how many sort of balls of radius epsilon would you need to cover this? Well, using a standard hexagonal covering argument, we can show that you need about 40 hexagons to cover this rectangle, or about 40 open balls. And for standard Euclidean space, of course, you can bound this as some constant times epsilon to the minus d. So the intuition here is that basically this is like a ratio of the area of the entire dotted rectangle to the area of each one of these hexagons. So the area of each hexagon scales like epsilon to the d. In this case, d is 2. This is just a two-dimensional case. Okay, so in this case, we can connect if we have this Holder continuity, we can connect the covering numbers of in the subspaces to the covering numbers of in theta space, which is much easier to construct, which ends up just being this n naught epsilon to the minus d over gamma. So you just have this gamma correction here. So for example, you would have something like n naught is roughly 3a to the d power times the covering number of capital theta using unit distance under this Euclidean metric. Okay, so generally, this is the property that we're most interested in. So we say that a parameterized subspace is said to be n naught d Holder regular if its covering numbers under this subspace metric satisfy this following inequality. So this is the covering using this subspace metric, which is just the spectral norm of the difference of projections at a radius epsilon, and we're saying that has to be at most n naught epsilon to the minus d. So really the key fact here is that the covering numbers grow at most polynomially with epsilon, as epsilon goes to 0, essentially. Okay, now let's talk about some specific sets of orthobases that obey these properties. So one is the Hermite orthobasis. So the Hermite orthobasis is basically a Gaussian function that is being modulated by polynomials of higher and higher order. So the first polynomial is 1, and then t squared minus 1, and then t cubed minus 3t, and so on and so forth. So the v4 is a fourth order polynomial. These c's are just arbitrary constants that are used to normalize these functions, basically. But it turns out these functions are all orthogonal to each other, and they're good for approximating sort of this irregularity, but they're generally very smooth. But sort of like they're great for approximating things that are relatively smooth but are also time limited, basically. And so you can construct a time-shifted orthobasis here that's just parameterized by the shift parameter theta, And so you have this set here. This is your set of all such subspaces that are just parameterized this way. And you can work it out. It turns out the n naught is about 64k cubed times this distance between the starting time and the ending time that you're searching over, this bounded parameter set. And d in this case is just 2, using basically gamma is equal to 1/2 in this previous slide here. Now this k cubed is believed to be a little bit loose, so probably there's an expression that you could probably get that would be k or k squared, something like that. But it's worth noting that it doesn't really matter that much. It's really going to be the log of n naught that's going to play a large role in our main results. And so in these sort of approximations that we're coming up with, we're fairly loose in terms of powers of k, for example. As long as we know that there's at least k to the 1 power, it doesn't matter if it's k cubed. Okay, so similarly, we can construct something for the lapped orthogonal transform. So basically, this is a basis that is constructed through this window function g of t. The cool thing about lapped orthogonal transforms is that you can stack them together and they remain orthogonal. So they're great for kind of piecing together lots of these sort of windows, these g of t type windows, side by side. You have basically a sort of even symmetry here on this side and an odd symmetry on this side that allows you to kind of merge these transition regions in a rather beautiful way. And so here, in this case, very comparable, n naught is 128 k cubed times the difference of this interval using a d equals to about 2. Okay, and last, there is this prolate spheroidal wave functions, which are essentially defined through this, this linear system. So in this system, you have a signal coming in, and it's time limited here using this projection operator onto a time interval of length t, and then it's frequency limited here at this operation using a frequency of omega. And so we define our orthobasis as basically just the kth eigenvalue of the system. And so the cool thing about that is that these, in some sense, capture most of the energy for things that are time limited and band limited. So here you can have a parameterized subspaces that are parameterized not only by this time shift theta 1, but also by this frequency shift theta 2. So this is basically moving this center point theta 1, theta 2 in this sort of time frequency tiling that we have here. And you choose k to be roughly equal to the time bandwidth product of capital theta and capital T. And then by doing that, you can account for most of the signals that lie in this space here. And you can sort of estimate how much of that signal you can account for by the eigenvalues of the system. As those the first few eigenvalues are very close to 1, and as those decay away to 0, you know that you're reaching diminishing returns, and you don't need to use a k much larger than that. And in this case, we're taking an n naught of just root 2 times. Essentially, this is like a time frequency product here and a time frequency product here, but this is over just this short time interval t and the short frequency interval omega multiplied by the full time interval here and the full frequency interval there, and using just a d equal to 2 for these 2 dimensions of this parameter. So now we're going to talk about, this is the main result here. So the main result is that for an n naught d Holder regularized parameterized set of k-dimensional subspaces, the functional error of compressive parametric estimation is not much larger than that of parametric estimation. So this, by definition, is the smallest error that you can get using any parameter, because it's, by definition, the minimizer. So this must be larger, but it's not much larger. And so it's larger by a factor that looks roughly like this. This is some universal constant times some square root of term that decays as 1 over square root of n, plus some other term that decays as 1 over m. And you have this expression here. Okay, so what does this mean? Well, if we look at this, we see that t must be at least d plus log of k n naught in order to make this expression less than 1. We see that the square root term dominates for large m, so as m becomes successively larger, this term will eventually dominate. And so we have this asymptotic decay with this oversampling factor that looks like this. So basically, this denominator is sort of the minimum factor of m that you need. And if you take m to be 10 times larger, 100 times larger, it basically rolls off like the square root of that oversampling factor, the inverse square root of that oversampling factor. So under these mild assumptions where n naught is greater than k and log of n naught is greater than d, we can simplify this even further to look like this expression. So this is very similar to a classical compressed sensing result that tells us that we need m to be at least k log n samples, where n is the ambient dimension. So here the main insight is that we're swapping out the ambient dimension for this base covering, basically. That's kind of the parallel there. So I'll give just a sketch of the proof to give you a basic idea of kind of what we're shooting for. So notice that these difference in errors can be written this way if you write them out. This is just the error for the compressive case and the error for the classical case. And you can simplify this down by adding in two extra terms. If you know that this by definition this expression here is by definition the global maximum of overall theta, basically. Then you can add this term in, and this term will be at least as large as its predecessor. And then by definition, this holds true. So we're just defining w theta to be the difference between this compressive term and this classical term. And so we can set this up as a supremum over all of these guys, over all theta with respect to some fixed theta. And of course that must be greater than this one, because this is one particular theta. So the supremum over all theta must be greater than some particular theta. So now it only remains to analyze this supremum of w theta. So what are some good tools that we can use to do that? Well, a natural one is chaining bounds. So chaining bounds are great for analyzing the supremum of Gaussian processes, but in general, they're also great for sub-exponential processes and things like this as well. So, taking a page out of Ledoux's and Talleyrand's book, we are mimicking kind of their approach to set up a very similar increment bound that's tailored for our Holder regular subspaces, basically. So the way this works is if we have some increment bound that looks like this is basically just saying that the probability that 2 points in this process are more than some function times the distance apart is at least some sub-exponential constant here. And this conv k function will be something like u plus square root of u. And so we have some constant Ca. So for that same constant Ca, and for any theta naught, any fixed theta naught inside of this capital theta, and then we're just going to choose this theta naught to be theta hat later, but for now, if we have these conditions, then we have this supremum bound that holds, basically. So this is a probability bound over the supremum over all such thetas. So this is essentially what we need. This is one of the main ingredients. All we need left, basically, is to establish a bound of this type, essentially, and that will allow us to make the whole case. How do we do that? Well, we can use what's called a matrix Bernstein norm. Bernstein norms are typically of the form where you have some summation of random variables that are given by some absolute upper bound, and you can give some tail bound on the sum of these random variables that is basically sub-exponential and looks something like this. And so Kolchinsky has this cool variation on this idea where it doesn't need to be strictly upper bounded. As long as it has sort of a soft upper bound through this Orless norm, then we're good. So this Orless norm is just defined to be basically just this infimum over all C, such that the expectation of the moment generating function essentially is less than or equal to 2, modulated by this C variable here. Roughly speaking, you can think of this as it's either finite when this variable is sub-exponential, so to speak, and it's infinite otherwise. And as long as this thing is finite, it usually is something like the mean of the random variable, the mean of the spectral norm of this random matrix, essentially. So these are the two main results, the main ingredients for the results. Now let's talk about some of the conclusions and open questions we have.